So in this video, we're going to discuss how you can graph the Arrhenius equation, because similarly to the integrated rate laws, which we've discussed previously, the Arrhenius equation can be written in a form that's analogous to y equals mx plus b. So if we take a look at the Arrhenius equation, we can see that k is equal to a, which is the frequency factor, times e to the negative EA, which is activation energy, over R, the ideal gas law constant, times temperature. So as I stated, we can rearrange this equation into a form that's analogous to y equals mx plus b. So the first thing we're going to do is take the natural logarithm of both sides, and due to the rules of natural logarithms, we're actually able to split up this natural logarithm of the frequency factor and the natural logarithm of the exponential factor. Now remember that natural log is the opposite of e, so actually these two functions cancel. So then we have the natural logarithm of the rate constant is equal to the natural logarithm of the frequency factor minus the activation energy over RT. Now rearranging this expression ever so slightly, we can see that the natural logarithm of k is equal to the opposite activation energy over R times the inverse of the temperature plus the natural logarithm of the frequency factor. So taking a closer look, we can see that this expression is analogous to y equals mx plus b. And so by plotting x versus y, which in this case x is 1 over temperature in Kelvin versus the natural logarithm of our rate constant k, we yield a linear relationship in which the slope is going to be equal to the negative activation energy over r, which is why we see a negative slope here, and the y-intercept is equal to the natural logarithm of the frequency factor. So from this plot, we can actually individually solve for the activation energy and the frequency factor of the reaction. So in this example problem, it states a plot of the natural logarithm of the rate constant versus the inverse temperature yielded a linear plot. And so we're given the equation of the line, which is y is equal to negative 1.12 times 10 to the fourth x plus 26.8. We're then asked to calculate the activation energy of the reaction. Well, if we recall the Arrhenius equation, we remember that this is analogous to the natural logarithm of k is equal to the negative activation energy over the ideal gas law constant times 1 over temperature in Kelvin plus our natural logarithm of the frequency factor. And so our slope with the units of Kelvin is equal to the negative activation energy over R. So by plugging in the value of R, which is the constant 8.314 joules per mole times Kelvin, we can actually solve for the activation energy by multiplying both sides by negative R. And so for this reaction, the activation energy ends up equaling 93,117 joules per mole. Now usually we'll express the activation energy in kilojoules per mole, so we'll need to divide by 1,000 joules in every 1 kilojoule, and so we would get the activation energy to be equal to 93.12 kilojoules per mole. Now the next question asks us to calculate the frequency factor of this reaction, and so we know that the y-intercept 26.8 is going to be equal to the natural logarithm of a. So in order to just solve for a, the frequency factor, we need to take the e of both sides so that the ln will cancel, and so a is equal to the value of 4.36 times 10 to the 11th. So remember, this value tells us that this is the number of times that the reactants actually approach the activation barrier per unit of time. There is also the 2-point form of the Arrhenius equation, You can actually derive this from the linear form of the Arrhenius equation. And this allows us to solve for, in general, the activation energy when we know the rate constant at two different temperatures. However, we could also solve for the rate constant at a second temperature or for the temperature of the second rate constant. So for example, in this problem it states that a reaction has a rate constant of 0.0117 inverse seconds at 400 Kelvin and 0.689 inverse seconds at 450 Kelvin. Determine the activation barrier for the reaction. So we're solving for activation energy E sub A. And so if we label this information as 1 and this given information as 2, we can plug in the values to the expression. So the natural logarithm of the rate constant 2, which is 0.689 inverse seconds, over rate constant 1, which in this case is 0.0117 inverse seconds, set that equal to the activation energy, which is what we're solving for, over our constant 8.314 joules per mole times Kelvin, times the difference of the inverse of our temperature 1, which is 400 Kelvin, minus 1 over 450 Kelvin. Now when you solve for the activation energy, you can actually determine this natural logarithm value and then divide by the difference of the inverse temperatures. Now when doing this, I get the value of 14672 in my calculator. Now the units at this point are Kelvin because we divided by inverse Kelvin, ultimately just leading to the units of Kelvin, and this is going to be equal to the activation energy over R, which is 8.314. So multiplying by R on both sides, we can get the final activation energy to be 121986 joules per mole. And like I said previously, we'll typically express activation energy in kilojoules per mole, so divide by 1,000, and this will give you 122 kilojoules per mole. Now the next question we're asked in this problem is, what is the value of the rate constant at 425 Kelvin? And so we already know the activation energy because we just solved for it. And we know that the rate constant at 400 Kelvin is 0.0117 inverse seconds. So plugging this information into the 2-point form of the Arrhenius equation, we have the natural log of our rate constant 2, which is what we're solving for, over our rate constant 1, is equal to our activation energy, which we do need to plug in joules per mole because our R value is in joules per mole times Kelvin. And then we're going to multiply by the inverse of temperature 1, which is 400 Kelvin, subtracted by the inverse of temperature 2, which we are trying to figure out the rate constant at this temperature, so 425 Kelvin. So first I would suggest solving this entity in your calculator. And we get that the natural log of the ratio of these rate constants at differing temperatures is equal to 2.16. And this is a unitless factor because joules per mole will cancel. And this Kelvin right here is actually the inverse of an inverse. So ultimately that just means that this has the units of Kelvin currently, which is going to cancel out with the inverse kelvins from this subtraction term. And so we need to figure out a way in which we can isolate just K2. So if we take the E of both sides, this will cancel out this ln factor. And so now we know that K2 over K1 is equal to e to the 2.16. So to isolate further and just solve for K2, we can multiply by K1 on both sides, and we get a final value of 0.101 inverse seconds for this second rate constant, which is at 425 Kelvin. And so it makes sense that this rate constant, which was at a higher temperature, is going to be a larger value than our rate constant 1, which is at a lower temperature, 400 Kelvin. So in summary, we've seen in this video that we can use the Arrhenius equation to plot data, and we can use the Arrhenius equation in the y equals mx plus b analogous form and even the 2-point form, and this enables us to solve for activation energy and the rate constant of reactions at varying temperatures.